So we had started talking about electric fields, and that's the idea that charged objects just change the world around them a little bit. If you put anything near a charged object, if that thing you put near it also has a charge, it'll be influenced by that charged object. And so we call that sort of influence that's baked into every charged object its electric field. It exists even if you don't hold anything up to it. It's something that's intrinsic to the charged object, just like every planet has a gravitational field, even if there's nothing that planet is pulling on. No one's living on that planet, for instance. How we measure the electric field is the only way we can. We do hold something up to it, and we see what happens. We measure the force on the little test charge we hold up to it, and then to make sure we get something that doesn't depend on which test charge we used, because the answer shouldn't change. It's not dependent on the thing you're testing with, it's dependent on the thing you're testing. To get rid of that effect of which test charge we use, we divide it out. And we call that result the electric field created by the object we are testing. So we looked at some examples of that and saw how you come in with your little test charge or the electric field inspector. You measure forces on your test charge at different points around the room. You divide by the size of your test charge, so you make sure your answer doesn't depend on which one you used, and you get the electric field. The reason that's useful is if anyone else comes along and asks you, well, what's the force on my charge going to be? You can tell them immediately. You say, well, you just take the electric field reading I took in the room and you multiply by your charge instead of mine. So it simplifies the process of finding forces because you only have to do the hard part of this once, which is finding that electric field. And we saw what it would be for a point charge, a little glob of charge. So this would be, you walk into a room, there's a big ball of charge in the middle, and you say, well, what influence does that have on the room around it? So you pull out your little test charge, you hold it up, you measure the force on it and see what happens. And what you find is that the size of that electric field will depend on how big that glob of charge in the middle of the room is, so the Q value, and how far you are away from it. And only those two things. As we see, it does not depend on the test charge you pulled out of your pocket to measure this electric field. That cancels out. So now, this is a different question. You walk into a room with multiple blobs of charge, and you ask, well, now what's going to happen when I pull my test charge out? Which way will it feel a force in this room? And you could go about that two ways. You could either directly measure it like that, find the force on your test charge, divide by the size of it, but that only works if those blobs are actually present in the room. How can we do it mathematically? Well, we combine what we know about how to find the electric field for those individual blobs. That's something we've already determined, this right here. And then we say the overall field that results, the influence these blobs of charge have on the room around them as a whole, comes from adding all of those fields up as vectors. How do you know that? Through lots of experiments, we've realized that vector addition does this for us. So that's the only justification for why I know I can add these as vectors. So that's what we were starting to do here. And essentially, we just went through and said for each charge, if I hold my little test charge up right here, what will each of those numbered charges do to it? We found that charge 1 would push it away, which is why we said the electric field for charge 1 is to the right. Charge 2 would attract my little positive test charge because it is negative, and so it's going to pull it towards it. That's where electric field 2 comes from. Charge 3 is also going to pull the little test charge towards it, so E3 is to the right. And then charge 4 is going to push the little positive test charge away from it, which is why E4 is away from charge 4. It's going to push little Q0 in that direction. So that's how I got all of those directions. Now I'm on the second part, which is adding those electric field vectors to get an overall electric field. And it is usual old vector addition, how we know and hate it from Physics 1. But we are now adding these fields, which each blob of charge is creating in the space around them. And we're going to add them up to find the net electric field in that room. Again, this is similar to Every planet creates a gravitational field around it. If we plop you at some point in space within our solar system, you're going to be pulled by different planets, pulled by Jupiter, Earth, the sun, all these different things. And so the question we're asking is, what is the net pull? But we want to get an answer that will be the same no matter which thing we're placing at that point in the solar system. That is the field rather than the force. The force depends on what you place at that point in addition to all the planets. The field just depends on the planets themselves. Really harping on this because it's an abstract concept for sure. Okay, tell me about electric field 1. What are its components?
Y would be 0.
Yep, it only points along the x direction. So what would I say about the x component?
Positive.
Yep. And since all of this vector points along the x direction, I don't need a sine or cosine. The entirety of E1 points along the x-axis. What about E2?
X is 0.
Yep. It points purely along the y-axis. So tell me about its y component.
Positive 5.
Positive direction.
Positive E2. So this does come up a lot. This is the charge. It creates that electric field, but that is not the electric field. It's like the mass of a planet versus the gravitational field that mass creates. They're different things. So just E2, because we don't know a number for it at this stage. All right, for E3, tell me about that one.
The x is positive.
What about the Y?
0.
Yep, so it points purely along the x direction. Still no need for sine or cosine. And then for E4, tell me about just left, right, up or down, so the signs of my x and y components. What's the sign for the x component? SIGN sign.
Negative.
Because it points to the left. And then what about the y component?
Positive.
Positive, it points up. Now we have to ask ourselves, how much to the left does it point? How much upward does it point? And for that, I need to sketch in my components. It points to the left by that much. That is E4x. It points up by that much. That is E4y. And those are what I have to now find the lengths of. And to do that, I need an angle. They told me this was 45 degrees. And so from that, I can infer that this is also 45 degrees. Because they are, I think it's called transversal angles. I forget the technical term for that, but it's just two crossing lines. If you look on either side of them, it's going to be the same angle. So how would I find E4y?
Sine.
Sine, because it is opposite the 45-degree angle. I got to go over there to it. And for opposite, we use sine. So E4 sine of 45 degrees. And then I know you can do it by process of elimination, but what should the x component be looking at our diagram?
Sine.
I think it might have cut off, but I assume cosine. It is, either because we already used sine, that's process of elimination, but also because this one is touching the 45-degree angle. It is adjacent to it. And we use cosine for adjacent. All right, now what do we do?
Do we add up the components?
Add down the column.
Yeah, this is still regular old vector addition. It's just with fields instead of forces now. Okay, now what? Well, step 3 up here, we have all of these different fields, and we know how much of each points left, right, up, or down, but we don't know the size of the field itself, how strong the field each charge creates at that location. For that, we use what we found on the previous page, that it depends on how big the charge is, and again, I'm using I to say it could be any number between, in this problem, 1 and 4, and then the distance from that charge to the point you're interested in, which is where the test charge is in this problem. So I need to compute those. This is step 3. K is this usual old number. And then my charge 1 is 2 microcoulombs, 2 times 10 to the negative 6 coulombs. And then I was nice in this problem. I said every charge is the same distance from that point. So this is actually R1, R2, R3, and R4. It's the same distance for all 4 charges. 0.06 meters. We square that, and I get 4.99 times 10 to the 6 newtons per coulomb. Again, newtons per coulomb you read as per each coulomb of charge I could put here, it will feel that many. So 5 times 10 to the 6. If I put 2 coulombs of charge there, it'll feel 10 times 10 to the 6 newtons of force. That's what the field is telling you about. It's like how concentrated forces are at different locations. So at this stage, you may look at this and say, this feels exactly like what we were doing at the end of the last chapter. And you would almost be correct. There is one tiny difference. What is the difference between what I'm doing here at the end of... Oh, I'm thinking of my other class where we have this split into 2 chapters. For us, it's the same chapter. What is the difference between what we did up here, so page 6, and what we are now doing on page 10? Because they look similar to each other, the processes, but something is a little bit different.
Were we looking for the force in the previous problem, and now we're looking for electric field?
Yeah, and in particular, what we notice is for this problem, there was a charge drawn here, and we're asking about what's happening to it. For fields, I'm asking about what's going on at a certain point in space. I can use a test charge to think about that, but there does not have to be anything present there. I'm reasoning about fields, which are things that just exist at every point in space around charged objects. And the reason I want to do this is because, again, this will let me answer the question of what would any charge I put here feel? What kind of force? All I have to do is take the field value I get and multiply by whatever charge I want to find the force on. Up here, I was only able to find the force on a single specific charge, a 4 microcoulomb charge. And then we got to this part at the end, and I said, well, what if you have to do it and I replace Q1 with a totally different charge? Then what? Your options are either go through all of this mess again, or you could do most of the work just once. That's finding the electric field. And then it's very easy for any charge you want to look at to find the force on it. So that's what we're doing. If you have a bag full of different charges you want to find the force on, when you put them right here, you could either do this same problem with all this vector addition, and it would be awful dozens of times, or you could do it a single time, like we're doing here, and then just multiply by the charge you're interested in finding the force on. This is the work we're saving by doing it this way. And this is the math reason fields are useful. Okay, I want you to calculate E2, E3, and E4. All right, does anyone have E2 yet?
I got 1.24 times 10 to the 7th.
Was it 1.24 something, like some change on that?
Yeah, 1.2486.
Okay, yeah, I'll just round it to 1.25, but I agree with you. So it's charge 2. Charge 2 is negative 5 microcoulombs, but again, the negative is not important. We already dealt with the consequences of it up here. It amounts to which direction E2 points. Now that we've dealt with that, we don't want to worry about it a second time. So we take absolute values. But we do get 1.25 times 10 to the 7. All right, what about E3?
I got 7.49 times 10 to the power of 6.
Sounds good to me. And I will give you E4 after I give myself a little bit more space for it. 9.99 times 10 to the 6th newtons per coulomb. And now I have enough information to actually compute these values. This is the x component of my net electric field, and this is the y component. So E net x is E1 plus E3 minus E4 cosine 45. And I just use the values I just computed for those. I'm not going to plug them in because it's just so much writing. But 5.42 times 10 to the 6 newtons per coulomb, and it is a positive value. Think about what that means, and we'll sketch it in a second. E net y is E2 plus E4 sine of 45 degrees. Again, we put in all those values we just calculated, and I get something like 1.95 times 10 to the 7 newtons per coulomb. Again, positive. What is the significance of those positives?
Would it be that the electric field is attractive?
Not attractive. What did positive and negative tell you about when we were finding these components up here?
Right or left?
Yeah, it's about directions. So this net electric field points to the right, and it points up. So if I go back to my original picture, I don't really have any primary colors left. So I'll just do a very thick green line to say this is what all of them amount to when you add those fields together. The net electric field points this way. In other words, if I put a little positive charge at that point O, it's going to go up and to the right in this room. If I put a little negative charge there, it's going to go down and to the left, opposite the direction of the field. And I know exactly how large the force on any of those will be. I just take the number I find for the net electric field and multiply it by whichever charge I'm interested in. So the last step is what we just did. We added up all the components, but then the very last bit is use Pythagorean theorem to put those together and get an overall strength for that electric field and an overall direction. And again, I like to use absolute values here to avoid confusion about negative angles. So that's my final step, and it will tell me exactly how strong this field is and exactly which way it points, what angle it makes with, in this case, the x-axis. So E net is all of this junk. And you get something like 2 times 10 to the 7 newtons per coulomb. And for theta, which I'll let you write the inverse tangent stuff if you like, but I get 75 degrees. So if I just take that part of the picture, this is point O. And again, the test charge was just a means of measuring the field here. It does not have to be at point O always. It was just a way I could test what was going on at that point. So what's happening at this point in the room, the electrical effect at this point is positive things tend to be pushed up into the right, negative things tend to be pushed down into the left. And this is 75 degrees. So I would interpret this as the net aura or effect of the 4 charges at this point in the room. And a charge placed here would feel a force of whatever its value is, Q, times the net electric field there. Any charge I would care to look at. Not a specific one, whatever I want. Whichever thing I pull out and place there, I can predict what's going to happen to it. So we are going to now think about every point in the room. I just found the electric field at a singular point in this room. If I wanted to figure out what's going on over here, I got to do everything I just did again, but for that point. What points away from charges, what points towards, vector addition, all of that stuff. Luckily, some people have done a lot of that work for us already. So for instance, if I have a singular positive charge, I know what'll happen if I put a little test charge, say, right here. What will happen to it? Which way will it be pushed? Towards or away from the positive charge?
Away.
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 Yeah. And so that is the influence of the big positive charge at this point in the room, is it tends to push stuff away if it's positive. It will tend to pull it towards it if it's negative. And that's true for anything I could place here. The test charge was just a way I could measure that. I could figure out what was going on there. So this is the electric field at that point, which let me make it a little bit more kind of directly away, as in like if I draw this line, it is along that line, pointing away from the big charge. And finding the value of the field at that point, that would be your job of computing kq over r squared a single time. That kind of sucks that it's that much work to do at once. But you might guess, if I move a little bit further away, I measure the electric field here with my test charge. How's it going to compare to the first one?
Is it going to be smaller?
Yeah, I'm further away, it's going to be weaker, but it will be in the same direction. And if I'm much closer to the charge, I'm going to see a stronger field. So what I'm noticing is these all point in the same direction along this line, they just have different strengths. So what I'm going to do is kind of start to be lazy and connect the dots and say, okay, well, generally along this line, the electric field points that way. Generally along this line, the electric field points this way. Generally along this line, it points this way, and so on and so forth. You would say it points radially away from that big charge in the middle. And we call these electric field lines. They're just, we got tired of computing the electric field at every single point in space, and we said, well, roughly what does it look like? What's the geometry? What's the shape of the electric field? And generally, for a positive point charge, it is like that. It just points outward everywhere around the positive charge. What do you think it looks like for a negative charge?
Same thing, except toward
Yeah, because
the charge in the middle.
the tendency of negative charges is to pull stuff in if it's positively charged. If we have a negatively charged thing we place out here, it's going to be pushed away, but still along these field lines. Kind of looks like a snowflake. And the number of lines I'm drawing is arbitrary. I could have drawn twice as many or half as many, but I need to be consistent at least about if this one gets, 8 lines, then an equal amount of negative charge should also get 8 lines. Okay, so that's what's going on here. Is these individual ones are my field vectors, my electric field vectors. These where I just connect the dots are my field lines. And they start to say more about what does the field look like everywhere around that charge, not just at specific points. And actually what you can kind of think of this as is, instead of electric field lines, like what influence it would have on charges, imagine that's the direction water flows. Then a positive charge is like a sprinkler or a fountain. It sprays out field lines in every direction. They are field line fountains. While negative charges are like a sink or a drain. Field lines flow into them. And so if you put a positive and negative charge beside each other, you might be able to kind of guess what that's going to look like. One thing is spraying the lines out, the other is taking them in, letting them drain into it. what I want to show you is that this is not just a kind of abstract thought thing, a way to think about charges. Fields are a real thing in that I can actually show you a picture of real stuff that looks like this. It's not going to be as pretty because other physics is going on, but I can show you that this is real. So the first thing I'm going to do is show you a not real version, a simulation, just to make sure the idea is clear. So I've got my singular point charge. This is before I've come up with the idea of field lines. And I just see what happens to it when I place it near that big charge in the middle. When I let it go, I see that it's pushed away. And that's true no matter where I put it. Anywhere around that big charge, it's going to be pushed away from it. So I'm going to say, oh, okay, my field must point away at every point. And if I want to get a better sense of the shape or the geometry of the field, I imagine doing this experiment over at lots of different points. And you start to see this radially away effect. And I could plot that in terms of the field vectors. They are stronger near the positive charge, so that's the white-looking vectors, and they get weaker as you move further away. That's why they get some transparency to say that they're getting weaker and weaker. But that's a lot to look at. That's kind of hard to picture. So why don't I connect the dots? There's my field lines. And that gives me a better sense of the shape of the electric field around this charge. If it's a negative charge, then the field lines look the same. It's just now they're representing arrows pointing in towards it, because that's what it would do to a bunch of little test charges I placed around it. It would pull them in towards it, right? And this animation is going to be up on Canvas because I think it's really cool. I did not make it, but we're going to use it to look at a couple of different scenarios here in a minute. But luckily, past me was smarter than present me, and I actually have these demos recorded because we had snow days a couple years back. So I want to show you this yet again. A couple different ways. Again, I'm really hammering the points home is what I'm trying to do. So first, that's called a Van de Graaff generator. All it does is just accumulates a lot of charge on that big metal dome at the top. That's its whole point in life, is to just accumulate lots of charge. And so that big metal dome is like our point charge, just a glob of charge. This tissue paper is my test charge. When I turn the Van de Graaff generator on, you're going to see it be pulled towards the Van de Graaff generator. And that gives me a sense of the electric field around the Van de Graaff. So you see when I hold it up, it's always pointing towards the center of the dome. That's a radial electric field, points towards the center of a sphere. All right, so that's imagining finding field vectors at individual points. I could instead do this at lots of points at once to get the idea of the field lines, the overall shape of the electric field. And we can do that by using lots of pieces of tissue paper instead of just one. And what you will see is a radial electric field everywhere around it. So those lines we drew represent a real thing. It's just a thing we can't see with our eyes unless we have a charged object to test it. And last, I have yet a different version of this, which is instead of using tissue paper, it uses little grass seeds, little semolina seeds. So that coat hanger piece dipped in the bowl is acting as my point charge. It's going to be the thing that is attracting and repelling the stuff around it. What it's going to attract or repel, what's going to act as my little test charges, these little grass seeds. They're going to be my test charge to say, what's the field look like here? And they're suspended in oil just so they can move freely. And what you'll see is, it's not perfect, but it is a radial field. It points outward away from this point charge in every direction. You see that nice radial field? The reason it's forming wings is because the seeds also have their own little electric fields, and they're attracting or repelling each other. And that's why we don't get a perfect, pretty picture like we would if there were really only one charged object in this bowl. So, for positive charges, the field lines always leave. They always point away from them, and they always enter negative charges. So they're away from positive charge, they are toward negative. Because that's what would happen to a little positive charge if we put it nearby. It would be pushed away from the big positive charge, pulled towards the big negative charge. And now we can start looking at, well, what if we have more than just one charge? Then what happens? We get something like this instead, more complicated field geometries. So on the left, we've got two like charges, and how you get these pictures is the same as how you get these. You find the electric field at each point around the objects, and then you connect the dots of them. It's just harder to do for these because you have to use vector addition. So for instance, right here, if I want to say, what's the direction of the electric field right there? Which way do you think it is? It's not drawn here, but which way do you think it points right there?
Up?
Up, just like the ones around it. So the question is, how do I get that mathematically? Well, that point is this far away from the left charge, and this far away from the right charge. I'm going to call this charge 1 and this charge 2. That electric field points away from charge 1, because it would push a little test charge that way. So this is E1. It's also going to point away from charge 2, because again, it's a positive charge. So that's E2. But when I add those two vectors together, which I could do using components, this one points to the right and upward. This one points to the left and upward. These components cancel each other out because they're of equal size but in opposite directions. The vertical components add together because they point in the same direction. And so my net electric field points up. So how I got this picture is I just kept doing that vector addition at every single point and then connected the dots to get these field lines. So it's not a pleasant experience to do, but that is how you could do it and how people did it at some point in the past. And I'll show you that that is a real field, a real shape a field can have. So these are two like charges, and you should see in the middle, they sort of form this no man's zone, this region where they don't want to let stuff be. And it's because the two positive charges are sort of fighting each other. Both are trying to push stuff away from them, and that means that stuff either kind of gets stuck in the middle or gets pushed out of it. And that's what we'll see is kind of a gap form in the middle. That's what I want you to look for in the video. You see in the middle, I'm not claiming it's a perfect looking field, but do you see how it looks like this one over here? If we have a positive and negative charge, then they form that bridge I was talking about, because the positive is going to push stuff away from it, the negative is going to pull stuff towards it. We call this a dipole. Equal amounts of positive and negative charge. And again, we get the picture the same way. If I wanted to find the electric field, say right here, because it's not drawn in this picture, well, it's this far away from charge 1, that far away from charge 2. I'll call this charge 1, this is charge 2. Charge 1 is going to push stuff away from it. I hold my little test charge up at that location, it's going to be pushed away from charge 1. So that's the direction of electric field 1. Charge 2 is going to pull stuff towards it. Hold my little test charge up, it would be pulled this way. So that's E2. Again, I can use vector addition to add them. This one points up and to the right. This one's down and to the right. So now the vertical components cancel each other out. The horizontal components add. So my net electric field points to the right. Just like all the other electric fields around it. You connect the dots. If I keep drawing these electric field vectors so they'd sort of look like this, you connect those dots, it's going to form one of those field lines. And I'll come back over here and say, okay, again, this is a real thing. So for unlike charges, you're watching for that bridge to form between them. One's positive, one's negative. Right? There's that bridge forming. And then on the outside, on the far left and far right, you're not seeing much going on. And that's because over here, the field lines spread out. They don't condense in like they do here to form that bridge. Okay, so field lines are showing you the shape of the electric field around the charges. And it is a 3D thing, so you can play with this more to see that, for instance, for a positive and negative is what I'm looking for. So there's my field vectors. But again, if I connect the dots, I see my field lines everywhere around the charges. Some other rules so that you draw these pictures right, which I'm not really going to ask you to draw a lot of them, but more you just have to be able to see what they're saying to you, because they actually give a lot of information about the field. For one, the field lines are always tangent to the electric field vectors. What I mean by that is, if I measure that electric field at lots of different points, and connect the dots, connecting the dots really just means that at the moment that field line reaches that particular point, it's in the same direction as the net electric field. It doesn't necessarily keep staying with it, keep staying in that direction, because it has to be able to curve towards the next direction of the electric field. So it's more like tangent, 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 but it can curve away after it's been tangent to the electric field. So this is my field line. And that's how I generate those pictures. The next thing is the number of field lines I draw should be proportional to the size or magnitude of the charge. So if I've got a positive charge, some amount Q, versus a positive 2Q, if this one gets 4 lines, this one better get 8. Because the field lines are reflecting how strong the electric field is around that object. And if we stick to that rule, we abide by it at all times, we will find that the closer the lines get, that corresponds to a stronger electric field. So, for instance, if I come back to these pictures up above, where should the field be strongest? Where are you expecting the most influence on charge if you put it where in this picture?
You would expect more influence closer?
Yeah, very near the charges. So, look, the field lines are denser there than they are out here. We have dense lines or a strong field. We have, what's the opposite of dense? Sparse, I guess, or a weak field. And then over here, you have Garfield. Field lines can't cross is the last rule. Why don't you think field lines can cross? Well, say they did. Say at a specific point in space, you got 2 field lines that cross. What would that mean about what happens to a charge that you place at that location? What's it going to do?
Would like a new field line be created or something?
Well, no, because the field lines themselves were already drawn from the net electric field. It's already accounting for that sort of additive effect of the two charges. So the field is drawn correctly in the first place by looking at which way does the net electric field point at each location in space. But this would actually be saying that the net electric field both points this way and this way at the exact same time. And not in the sense of, oh, those are just two vectors, add them together. No, as in like it's a 50-50 shot which way the charge will go when you place it there. See how that's a problem? They can't cross because then we actually have no clue which way the electric field points at that location. It's not a deterministic thing. And from experiment, we expect electric fields to have a precise direction at every point in space. We don't expect them to guess at each point and say 50% of the time I'll send charges this way, the other 50% I'll send them this way. That's the problem. If lines crossed, field would point in two directions at once. And we'd have absolutely no idea which way charges actually go at that point. It's sort of like, it's the same issue as saying, at this specific point in a stream, in a river, there's a 50% chance that water flows this way, and there's a 50% chance that water flows that way. We don't expect that in a river if it's reached this steady state flow where things aren't changing. It shouldn't just be flip-flopping between those two different options. So, field lines can't cross because we need a definite direction for the electric field at every point in space. All right, we'll do this example next time. We'll talk a little bit about the heart, and then we'll get into the worst part of the chapter, which is Gauss's law, because if electric fields are abstract, Gauss's law is hella abstract. So look back over electric fields. If anything was confusing today, I urge you, because really, it just gets worse from here if they don't make sense. Any questions on anything then?
Are you gonna put all the finished notes up also?
I really only like to do that for prior to exams, so a week or two before an exam, just because if I'm posting every day these notes, I mean, there's a recording and there's 40 other people in the class. The other reason I don't post notes, by the way, for when we're in person is because people stop showing up historically. That's just what happens. I'm not claiming any specific person. I'm just saying there tends to be like a 20 to 30% drop off if I start posting notes.
Yeah, I was just saying it because, like, a lot of the information I want to make sure I have right.
Oh yeah. No, I know you're doing it for the right reasons. I'm just saying that's why I don't tend to do it. But the recording will be up later today. I mean, you can actually see right now there's 22 people and it's a 45-person class, and I think it capped at like 28. So when notes are available in any form, we don't tend to see people.
That is true.
Are the physical demonstrations you showed on Canvas? Good question. I may have uploaded them at some point in the past. I'll double check, but if they're not, I will put them up.
I had a question about like the online work, like in Wiley.
Mhm.
So I saw that there's like a practice thing on there,
Mhm.
but that's like for the entire chapter. Um, are there other assignments on there that we also need to be completing as well?
So
Or I'm
there's
just a little confused about like which ones are part of the grade and which ones are not.
yeah,
If that
so
makes sense.
if you go to what's called the Canvas page guide, it's
Mm-hmm.
that very first module. It tells you exactly what is graded and what is not. Um,
Okay.
but just to recap it, it's 2 assignments are truly graded for you, and that's the pre-lecture videos and the
Okay.
homeworks.
Okay.
Everything else is either practice, so the ones that are called practice are just like if you want some extra practice for quizzes, especially, is where that helps.
Mm-hmm.
And then the adaptive practice is extra credit, and it's not due until the end of the semester if you want to do it.
Okay. Are I'm looking at the module right now. Is the adaptive practice something we access through Wiley, or is it going to be
It's all on
linked in the
Canvas.
module?
Yeah, all on Canvas. So you never touch Wiley course resources except for to get to the textbook.
Okay. I don't see the adaptive practice for this chapter. Maybe I'm overlooking it.
Let me see.
I see the reading, animations, physics, demonstration videos, practice, additional examples, and then pre-lecture videos.
Let's see. So that would be because I haven't put it up yet. It's up
Okay.
now. Sorry about that.
No problem.
All right. Any other questions? All right. Well, if not, y'all have a good day, and I will get this posted later after my second class and another meeting, so maybe a little bit, but I'll get them up.